So yeah, hi guys, I'm Kev. I'm a final PhD student at the University of Leeds, and this is some material from the final chapter of that thesis, which I'll hopefully be defending in a couple of weeks' time, so I'm quite keen to hear people's opinions on it. It's all really fresh stuff. But before we get going, my collaborator on a different project, Simon, can't make it this week because of the rail strikes, but he does have a poster, so please do go check that out. It would have been in this session. You can find it on the Slack channel, or you can chat with me about it. I'm very happy to go through this code that we've written, or you can read the paper, which you can find through that QR code there, but given that no one's got their phones out and is scanning it, I may as well just continue. So today I'll be talking about continental rifting. It's the breakup of very strong continental lithosphere to form new ocean basins. And this is a process which is incredibly variable through its evolution. So on the left-hand side over here, what we have is a classic example of an early stage continental rift, where the crust and the lithosphere still remain quite thick. And what we have are large faults along the flanks of the rift, which accommodate most of the extension. And this is where we get the bulk of these early stage rifting volcanoes. We know that eventually it evolves into a mid-ocean ridge, which is what's seen in subfigure C over here, where all the deformation and volcanism is now focused in the center of the rift, and the crust and lithospheric mantle are pretty much completely obliterated. There's no more border faults active, they're just completely sat to one side and abandoned. What we have in the middle is a late stage continental rift, which can't really make up its mind on where it wants to be right now. The crust and lithosphere still remain super thick. All the deformation and volcanism, however, has now migrated to the center. And with this migration, what we also get is a shift in the extensional regime. So rather than all the deformation occurring along the flanks of the rift, we now have deformation occurring in the center of the rift. And that deformation is accompanied by dike intrusion, which takes up most of the extension accommodation. And understanding the nature of this dike intrusion, the way dikes can take up not only the extension in the center of the rift, but also affect the rheological properties of the crust through having a lot of hot stuff in the middle of the crust. Needs to be studied a bit further if we want to understand how continents evolve through geological time. And yeah, just to see what kind of processes might be active concurrently with the rifting process. And there's no better place to study it than the East African rift system. So you can see here, it starts off down here in Mozambique, where there's barely any volcanoes. It's still in a very early rifting stage. And the moment we hit Kenya, we start getting volcanoes and faults marking out the flanks of the rifting region. Once we start moving into the Main Ethiopian Rift, the MER over here, we now get a lot more volcanism and deformation in the center of the rift, which occurred from 1.8 million years ago, it's believed. And then at the Afar Depression, we meet the Red Sea Rift and the Gulf of Aden Ridge, which gradually evolve into two mid-ocean ridge systems, which Emma can tell you more about. So my study area is the Main Ethiopian Rift, which is this awkward hybrid stage, which can't quite make its mind up just yet. And we observe dike-induced rifting at Afar in Iceland. And the question I decided to pose myself was whether or not we could collect materials from the Main Ethiopian Rift, because we don't really have that much recent evidence of dike intrusion within this portion of the rift, and whether or not we could maybe mix and match some different processes up from these different settings and see whether some processes are active in the Main Ethiopian rift and whether they're not active, and how do they compare with other rifting areas of the world. So I went over there in 2019 and collected some samples. The samples are collected from East Zy, which is this left-hand side, and also from the Boku Volcanic Complex, which is the right-hand side. And these are two monogenetic cone fields. East Zy is found about half a degree of latitude south of Boku, and so it's believed to be a less mature stage of rift evolution. You can mark out these scoria cones actually quite nicely from these digital elevation models, where they're associated with these basalts, and also with some faults which strike northeast, southwest, roughly subparallel to the overall trend of the Main Ethiopian rift. And from these scoria, I collected some olivine crystals, and these are some really weird things. So I'm going to take some time with this figure. So these crystals can be subdivided into two kinds of crystals based on their compositional zoning. So we've got A over here, which is normally zoned. You can see it's got quite a dark core in the grayscale, which is representative of a high magnesium crystal. And then around the rims of it, you can see it's quite light, it's quite bright, and that's reflective of high iron, low magnesium. This is in complete contrast to crystal B, which is shown over here, which has a low magnesium, high iron core. And then you've got this very dark rim running around the outside, which is zoomed in a bit further in subfigures C and D. So what we've got is a very high magnesium rim running around the outside of our crystal, Looking at this particular part of the rim, what we can see is that the reverse zone part of the rim, this bit which goes from low magnesium to high magnesium, is fairly straight, but also quite diffuse. It's not a very sharp boundary. It's quite straight, and so we believe that this might have represented some kind of olivine paleo rim in the past, which then has had a stage of overgrowth, which forms this normal part of the rim, which you can see is quite wibbly wobbly in the overall compositional gradient of the part of the crystal in this part, and is quite jagged, suggesting that it might have grown under some undercooling. And finally, it's worth pointing out that A and B are both collected from the same material, from the same cone. So we're getting these two very distinct populations pretty much in the same space. So what I've decided to do for this project, with my supervisor Dan Morgan assisting me quite a bit, is use cationic diffusion in these minerals to act as a geochronometer. So assuming that growth is very quick, what we can assume is the initial condition is basically a vertical jump from one composition to another composition over geological time. If this sits around for quite a while, this initially sharp condition will eventually start smoothing out, producing this sigmoid over here. And by comparing model sigmoids to sigmoids we observe by looking at my crystals, we can then have an idea of what kind of timescales are likely to produce those shapes. And that's what we've done here. We've collected some probe data points, which are these red dots on these compositional profiles, and we've matched them up to some grayscale backscatter profiles using Python minimalization. And as what's come out is basically these profiles. So on the left-hand side, we've got our normal zoned olivine, where we've got a high magnesium core over here, and a low magnesium rim over here. And then here we've got our reverse zoned olivine, which has got a low magnesium core and a high magnesium rim over here. It's worth pointing out at this point that this part, I'm going to term the reverse part of this reverse rim, and in this part is the outermost growth affected normal part of this reverse rim, just because things might get a bit confusing down the line if it's not already confusing. Right, so let's look at some compositions. So these are some crystal compositions collected from Boku and also from East ZY. So as is in real life, Boku is found to the north of ZY, which is down here. So first things first, we can see that normal zoned crystals and reverse zoned crystals are present at both of these two distinct rift settings, which are separated by half a degree of latitude. So clearly there must be some processes which are quite common to both these particular parts of the rift. Here we can see the normal zoned crystals cores and the reverse zoned crystal rims are both the furthest out of equilibrium with the carrier melts which brought them to the surface, with the rims of Boku normal crystals and also of ZY normal crystals, and the cores of the reverse crystals and the outermost part of those reverse crystals being most in equilibrium with the carrier melts that brought them to the surface. And that's kind of bizarre, actually. It's kind of weird thinking about how you've got a core which is in equilibrium with a melt, and there's this bit in between separating one from the other. Right, so for some timescales, what we've got here are some diffusional profiles that we've then fitted with model profiles. And yeah, again, we're seeing something quite eerie. We're seeing that between Boku and between ZY, we're getting quite a nice match. Despite these compositional differences, despite this latitudinal difference, we're getting quite similar processes occurring. So on the left-hand side, what we have are normal zoned olivines, and you can see there's a very almost gradual peak over here, but it's a bit sharper in the ZY crystals, peaking at about 100 to 300 days. There's almost a secondary peak here in the ZY distribution, corresponding to about 1 to 10 days, which is, you can almost sort of squint at it over here in the Boku distribution, but it's kind of hard to tell. We need a bit more data there. The reverse part of the reverse zoned olivines has a very distinct peak at about 30 to 100 for Boku, and it's quite similar in ZY as well. And then the reverse zoned olivines outermost normal part, because we're assuming that it's diffusion, if it is growth, then these diffusional timescales, because they act on such a longer time scale than the growth does, should act as maxima rather than anything like concrete. So looking at these, what we can see is there's a maximum time scale potentially of about 1 to 10 days. It's quite short compared to everything else. But of course, what you can see is that everything is roughly stacked on top of each other for these individual parts of each profile. And yeah, what we can see is that there are clearly some processes active on similar timescales, similar in their compositional nature to each other at these two different settings. And if we were to take all of our timescales and stack them up with each other and compare the maximum timescales to what we get from dike intrusion intervals at the Bahu and Krafler, we can see that the maximum timescales we get quite neatly actually line up with the timescales of dike intrusion during active rifting episodes at the Bahu and at Krafla. So that might suggest that perhaps there are common, maybe even generic controls on dike intrusion at these two settings. This is the most hand-wavy part of the entire chapter. So yeah, I'm just curious as to what people might think about this. As a result, we've developed this conceptual model of how we think this all fits together, this very complex compositional temporal history recorded by our olivine crystals. So we believe that there's already some melt already in the mid-crust. We know they're in the mid-crust from a previous study that I've done. And at some point, this is just blasted by melt from a lower reservoir or from the moho. This new melt coming in is high magnesium, and with it comes some high magnesium olivines. And it's like living with your ex in an apartment. It gets very uncomfortable for everyone involved. So what we have is the growth of high magnesium olivine rims around the olivines that are already present in the mid-crust. So that's their way of expressing this equilibrium. And then the way these high magnesium olivines, which have been derived from the lower parts, express this equilibrium is by developing normal rims to equilibrate with this newly mixed sort of hybridized melt. After sitting around for a few hundred days, what we have is the development of these diffusional profiles that we can observe compositionally. And then in the final stages, possibly triggered by another dike intrusion, what we have is a second stage, which brings in yet more normal zoned olivines, or I should say high magnesium olivines, which get normally zoned on their way up to the surface. And that's why that second distribution we see in the ZY normal zoned olivines are quite similar to the short timescales we get, which are believed to be growth affected. Right, so to summarize everything, I've put this graphical abstract up on Twitter. Just a quick shout out to my collaborators on this project who have been incredibly helpful for the past few months of my PhD while I've been stressing to get everything done. And yeah, thank you for your time. And as I said before, do check out Simon Matthews' poster as well. Cheers, guys.